Thermal factor of aluminium high-pressure die casting container, mold, to achieve 6 sigma quality of castings. Abstract. This paper deals with the analysis of the temperature factors of aluminium high-pressure die casting container, mold. It also describes the development of expression for preheating temperature factor of mold to maintain the molten aluminium temperature, which gives the 6 sigma quality product depending on the degree of preheating of mold. The monitored temperature factors are very much important in the die casting process, which is positively reflected in production efficiency and the quality of the casting. In die casting, the melted metal is pressed under high temperature into a mold cavity of significantly lower temperature. The mold is then exposed to a thermal strain of individual surface layers of the mold material. The speed of cooling of the castings in the metal mold increases, causing an increase of thermal gradients in the casting. Intensive heat exchange between the castings and the metal mold harms fluidity, which increases the danger of incomplete replenishment and the occurrence of cold joints. Analysis and optimization were performed with the help of ProCast Simulation software, which uses Finite Element Analysis Technology. Keywords: high pressure die casting, Hpdc, preheating temperature, 6 sigma quality of a casting, ProCast. Introduction. Die casting is amongst the highest volume, mass-produced items manufactured by the metalwork industry, and they can be found in thousands of consumer, commercial and industrial products. Aluminium alloy is the light in weight while processing high-dimensional stability for complex shapes and thin walls. Even in a completely controlled process, defect in casting are observed, and hence casting process is also known as a process of uncertainty that challenges explanation about the cause of casting defect. To identify the casting defect and problem related to casting, the study is aimed at research work. In today's world, a casting production without any defect is almost impossible, so all the process parameters that contribute to casting rejection were studied. Critical parameters like thermal, temperature of molten metal, mold, filling chamber, and pressure, intensified, clamping, were taken for the analysis. This temperature depends on the temperature of the material, the quantity of the metal, the method of the cooling of the casting mold, the thermal conductivity of the mold material, and the time during which the casting remains in the mold. The current rejection level in casting is around 11 to 13%, so the attempts are being made to bring and keep the rejections in the die casting process as per the 6 sigma limit 1. Various defects such as porosity, blowhole, improper filling time, hot spots, and misruns in the castings were properly studied. 2. 3. Analysis and optimization of the preheating temperature of mold were performed with the help of ProCast Simulation software. Die-cast parts are important components of products ranging from toys to automobiles. Parts can be as simple as a sink faucet or as complex as a connector housing. Die casting is one of the fastest and most cost-effective methods for producing a wide range of components where molten metal is injected into a permanent mold at high speed, 10 to 100 m/sec, and under high pressure. However, to achieve maximum benefits from this process, it is important to maintain the critical parameters of the process. 1. 5. Despite recent scientific research engaged in the issue of die casting, many factors and problems related to this technology remain unexplained. It also refers to the study of the impact of thermal factors of casting on the quality of the castings. 2. Literature review. The global market is becoming more and more quality conscious. To compete in such an environment, companies need to adopt an efficient technique that can assess and take a diagnostic approach to meet customer needs and expectations. Nowadays, the industrial world has realized that the Six Sigma philosophy is certainly a viable solution to their shop floor problems. 1. The quality of casting is influenced by many thermal and technological factors, the basics of which are temperature of cast alloy, the temperature of the filling chamber, and the temperature of the mold. This temperature depends on the temperature of the material, the quantity of the metal, the method of the cooling of the casting mold, the thermal conductivity of the mold material, and the time during which the casting remains in the mold. 3. 6. Die casting of metals are the highest technological level of metals and their alloys casting into metal molds. The quality of pressure die castings are affected by numerous technological factors, such as pressing velocity during a casting cycle, increase pressure, and time of filling a mold cavity. 7. A stable finite difference scheme, the component-wise splitting method, a 3D thermal analysis system has been introduced and adopted in the mathematical modeling of the heat transfer problem in the die casting process. 8. To improve the mechanical properties of aluminum alloy parts, the semi-solid die casting process is used in the manufacture of automobile components. Semi-solid die casting has a different die structure from those of general die casting and squeeze casting. Because the oxide skin is produced during the reheating process will cause defects when it fills the die cavity. In semi-solid die casting, the most important factors are the filling velocity, the area of the gate, and the position, size, the number of overflows. 9. Product manufactured from every manufacturing process shows some defects. For supplying a quality product to the customer, these defects must be reduced. There can be defects in a die-cast product like porosity, blowhole, non-filling, etc. If they are within the control limit, then the product is acceptable, otherwise rejected. 3. Every manufacturer tries to manufacture defect-free components, but practically it is not possible, and some defects remain in the component and lead to rejection of the component. This rejection can be minimized upon a certain extent. Different methods can be used to minimize defects. Some of them are, by improving process parameters, by design modifications, or both. 10-11. Determining the optimal process parameter setting will significantly improve the mold yield, output ratio of metal, shorten manufacturing period, save energy and resource. During the injection of molten metal, the flow inside the shot sleeve before plunger should be laminar. If these speeds, the injection pressure, is not set properly, the flow of metal will be disturbed and convert into turbulence, and there will be a possibility of formation of porosity during the process. Pouring temperature generally varies from 650 to 800 degrees Celsius. Generally, a better fluidity in higher temperature is connected with the preheating is done to remove the possibility of formation of temperature gradients. If we increase the preheat temperature from a particular range, then it may affect the die coating, and also it may create defects like rough surface finish, and also if the temperature is removed considerably, then this may cause a particularly chilling effect, which in turn leads to less solidification of core, and due to this difference in solidification rate, defects like solidification shrinkage may occur, decreasing viscosity. 12. With changing times and increased competition, it has become mandatory to reduce the rejection level in the die casting process. After studying the literature review, it was found that a lot of work has been done on the hydraulic die casting process one way or another. Literature reveals that a lot of work has been done optimization of the die casting process. 13-14 Redesign the gating and runner system to increase the overall efficiency. 5. Optimize process parameters using Doe and Taguchi methodology. 1-11 Flow simulation of the die casting process, modeling and simulation of alloy steel casting. 15-16 Thermal factors affecting the die casting process. 17, etc. Based on the literature survey and the subsequent analysis of gaps, the present work aims to investigate the effects of thermal factors in a die casting process on the quality of cast product and optimize the process using ProCast Simulation. 3. Process parameters. The hydraulic die casting process is governed by its process parameters, so it is required to study its process parameters and its effects. Mostly casting defects are concerned with process parameters. Hence one has to control the process parameter to achieve zero defect parts. The metal flow in the die castings is influenced by the pouring temperature, die temperature, and the thermal conductivity of alloy. In a typical die casting machine, the molten metal is poured in the shot sleeve through a ladle after the die is closed. A movement of plunger, piston, forces the metal through the die, resulting in that the movable part coincides with the fixed part. Various process parameters. In a practical die casting process is quite tough to judge the exact cause for a particular defect because they are quite intuitive, so first of all, it is required to identify process parameters that can affect the process considerably and can change the output with reasonable weight. A cause and effect diagram is drawn for casting defects as shown in Figure 1a. Pressure die casting essentially consists of following parameters such as pouring molten temperature, preheat temperature, filling time, riser design, plunger velocity, die holding time, injection pressure, die coat material, solidification time, die coat thickness, cooling system. Fig 1, cause and effect diagram for casting defects. The process parameters which are critical and can affect the process considerably for producing defective castings are pouring temperature. Pouring temperature generally varies from 650 to 800 degrees Celsius. When we pour aluminium alloy, then its fluidity is completely dependent upon pouring temperature. Generally, a better fluidity in higher temperature is connected with the decreasing viscosity and surface tension of molten metal with the increasing of pouring temperature, which leads to the increasing filling speed. At the same time, the heat capacity of molten alloy rises with increasing temperature of the pouring, what increases by filling time. The pouring temperature also affects the microstructure formation to a greater extent, and which in turn affects the final structure and toughness of casting products. Preheat temperature. Preheating in the gravity die casting is done to remove the possibility of the formation of temperature gradients. If we increase the preheat temperature from a particular range, then it may affect the die coating, and also it may create defects like rough surface finish, and also if the temperature is removed considerably, then this may cause a particularly chilling effect, which in turn leads to less solidification of core, and due to this difference in solidification rate, defects like solidification shrinkage may occur. A significant precondition for the production of high-quality castings by keeping an optimum temperature of the respective parts of the mold cavity surfaces. Injection pressure. This is the pressure that causes the material to flow, and it may be approximately measured by a transducer located in the hydraulic line or the nozzle. There is a direct relationship between injection pressure and injection line pressure. This is the primary pressure for injecting 95% of the molten metal into the closed mold. Normally, the highest pressure and fastest fill rate are the best conditions. Clamp pressure. The only reason to have clamp pressure is to keep the mold closed against injection pressure. Therefore, the amount of clamp pressure required is based on the material being molded. The easier flow materials require less injection pressure, thus they require less clamp pressure. Conversely, the stiffer flow materials will require more injection pressure, thus more clamp pressure. Holding pressure. Once the majority of the molten metal, 95%, has been injected using standard injection pressure 18, the machine should drop into hold pressure. This pressure is about half of the injection pressure and is used to finish filling the mold by packing the molecules together in an orderly fashion. Hold pressure is required until the gate freezes off, normally in 3 to 4 seconds. Once that happens, hold pressure has no more effect on the molecules on the other side of the gate. The temperature of mold. The casting quality is significantly affected by the temperature regime of the mold. When the mold is cold, joints are formed in the casting and the surface quality of casting is insufficient. When the mold is very hot, the alloys are bonded to the mold and the amount of bubbles and pores grows. The temperature of the mold will be maintained constantly at approximately 1/3 of the temperature of the cast metal. This is achieved by thermoregulation of the mold. The temperature of a filling chamber. When the chamber is preheated before the casting process, the temperature of the cast alloy does not decrease before filling of the mold cavity. 19. The increased rate of cooling of castings in a metal mold in comparison with a sand mold causes an increase in temperature gradients in the casting. 4. Development of preheating temperature equation for Hpdc. A significant precondition for the production of high-quality castings is keeping an optimal temperature of the respective parts of the mold cavity surface. This temperature depends on the temperature of the material, the quantity of the metal, the method of the cooling of the casting mold, the thermal conductivity of the mold material and the time during which the casting remains in the mold. The following applies for the thermal balance per one cycle. Q1 plus Q2 Q3 Q4 equals Q1. 1. Where Q1 equals is the amount of heat required for preheating of the mold. Q2 equals is the amount of heat injected by casting. Q3 equals is the amount of thermal energy transferred from the casting to the mold. Q4 equals is the amount of heat minus the heat of the mold leaving the casting. Equation 1 becomes Q2 Q3 Q4 equals 0. 2. Then the amount of heat injected by the casting, Q2. Q2 equals PL, L plus PS, 423.3. 3. Where W equals is the weight of casting plus 0.6 of intake weight kg. CPL equals is the specific heat of molten aluminum. kg. TL equals is the temperature of the liquid aluminum. Ts equals is the solidus temperature. L equals is the latent heat of solid aluminum. kg. CPS equals is the specific heat of solid aluminum. kg. The amount of heat transmitted by the casting to the mold, Q3. Q3 equals AA, TLTM, T. 4. Where A equals is the heat transfer coefficients Wm2K1. A equals is the casting surface M2. Tm equals is the temperature of the mold. T equals is the cooling time, S. The amount of heat leaving the mold with the casting, Q4. Q4 equals WCPS, T220. 5. Where T2 equals is the temperature of the casting taken out from the mold. The heat balance equation, 2, as follows. Q2 equals Q4 plus Q3. 6. Substituting 3, 4, and 5 in equation 2, we get equation 7 will be used to find out the preheating temperature required for the mold container, which depends on the weight and surface area of the casting, specific heat of the molten and solid aluminium, temperature of the molten and solidus aluminium, latent heat of solidus aluminium, heat transfer coefficient and temperature of casting when taken out from the mold. Experimental validation. The above heat balance equation validation was carried out by simulation using ProCast software. The experimental setup consists of high-pressure die casting machine of 100 T, a diesel-fired holding furnace, and a closed-loop cooling system. The die-cast rotor 100s, M50 and B48, which is used for the motors, product selected for validation, which varies its diameter from 50 mm to 250 mm and length varies from 25 mm to 300 mm. Validation for the die casting of 100s and M50 frame rotors. Fig.2 shows the meshing of 100s and M50 rotors. Therefore the preheating temperature of the mold required is 76.33. To balance the heat cycle resulting in 6 sigma quality rotors. 6. Simulation and results. Monitoring of mold temperature. The evolution of the mold temperature during the preheating cycle simulation for M50 and 100s frame rotor can be observed in Fig 3 and Fig 4, during each simulation. It was observed that temperature was attaining peak point of 475 degrees C, which directly affects filling time. The temperature of the mold can control by regulating the flow of the cooling system through the mold. Fig.5 and Fig.6 show the mold temperature at a variable flow rate of the cooling system. So every time preheating is not required, we can set the required flow to maintain the mold temperature. The temperature of the mold is maintained for minimum filling time and life of the mold. Simulation of the preheating, without preheating temperature cycles and filling time. The same results were validated by ProCast Simulation. Software. Table 1 shows the initial conditions for the simulation cycles. Table 2 shows the simulation results for filling time for M50 and 100s frame rotors. The main input to the ProCast simulation is the structured mesh geometry of mold containing part cavity, feeders, gating channels, cores, chills, insulation, etc. Along with the relevant material properties, density, specific heat, thermal conductivity. The geometric elements are created during methods design functions in ProCast, and the property values are taken from a comprehensive database of casting alloys and other materials. Other important parameters include the appropriate boundary and initial conditions, filling time, and pouring temperature. All inputs for M50 and 100s frame rotors are provided, and the filling time before and after preheating was computed. Fig 7 and Fig 8 shows the simulation results for 100 seconds and M50 frame rotors for filling time with preheating and without preheating. 7. Conclusion. The present study is an attempt to tackle one of the thermal factors, preheating temperature of the die casting process based on the thermal cycle of the die casting. Work is aimed at the evaluation of the impact of thermal factors preheating temperature on the quality of the Hpdc product. The result of the balanced thermal equation shows good agreement with the available data for different sizes of the casting on the Hpdc machine. 1. According to the simulated analysis with preheating without preheating temperature and filling time, it is observed that the filling time is less in case of preheating temperature. The thermal balance equation is beneficial to improve the thermal parameters, predicting the defects related to the filling process, as to achieve the Six Sigma products. 2. It is observed that the preheating temperature evaluated from the thermal equation should be maintained throughout the die casting cycle by maintaining the flow of the cooling system into the container. 3. Using a heat balance equation and finding the preheating temperature waste shot can be eliminated.